Hello, I'm going to be talking in this presentation about stability in heterogeneous multi-agent centrality games. This is joint work with my colleague Cosmin Bonkish. In this paper, we're interested in the concept of centrality measures in networks. Here is a well-known picture of relationships between Florentine families, and a centrality measures the position of a node in a network. So there are various such measures that have been investigated. Three sample ones here. Degree centrality, which is basically just the degree of a node suitably normalized. Between centrality, which measures the extent to which the node is on the shortest path between two nodes in the network. So sigma xz is a number of shortest paths between x and z, and the denominator is the number of such paths, shortest paths that go through node y. Eccentricity centrality looks basically at the farthest node in the connected components of x, the farthest from x, and it's suitably normalized and inverted. Other kinds of measures that we're interested in have a game theoretic flavor. That is, we have a coalitional game on a network where nodes are the players, and the centrality measure of a node arises as a Shapley or Banzhaf value of the game. A particular important example is the so-called Mihala game theoretic network centrality, which is basically the Shapley value of the game, where the value of a coalition of nodes is given by the number of nodes in the coalition plus the number of neighbors. So this is a measure that has been well studied before and has a nice closed formula. And we're also going to be looking at the Banzhaf version of this measure, which to our knowledge was only introduced in this paper. What do we do with centrality? Basically, we're looking at networks that form strategically. You have an agents, and they want to form a network by adding or dropping edges. Each agent is strategic. It wants to maximize its centrality subject to the cost of edges that it maintains. Each edge will be costly. It will have a small positive cost. This basically models the phenomenon of weak ties in the sense of Granovetter. And most importantly, the model is heterogeneous. Different agents may want to maximize different centralities. And given that we're talking about a model that is quite general, one can ask, can we prove anything meaningful about such models? Can any interesting class of network arise from such a model? And we can also ask kind of a reverse question. Given the emerging network, can we say something about what was the objective of an individual node if we look at the set of networks that emerge? We're not going to be talking in this presentation about all the results in this paper. So here are a couple of formal details. We're looking at the generalization of the well-known Jackson-Walensky model from economics. You have an agent. Each agent has a centrality measure, C1, C2, Cn. And these centralities are subject to thresholds, theta 1, theta 2, theta n. These can be either positive real numbers or plus infinity. Basically, an agent doesn't care about its centrality being over theta I. The utility of a given agent is given by the value of its truncated centrality minus the total cost of the edges, which is just epsilon times its degree. Of course, this generalizes the Jackson-Walensky model when the centrality measures are the so-called decay centrality and the thresholds are plus infinity. Agents can unilaterally drop an existing edge when it benefits them to do so. To add an edge, the edge addition has to weakly benefit both of them, and it has to benefit at least one of them strictly. And the central stability concept that we're looking at in such a model is that of an asymptotically pairwise stable network, or APSN. We're going to call a network G APSN when no move is improving in the sense of edge addition or removal. Of course, this is going to be true for small enough values of epsilon. So we're going to deal with um, agent heterogeneity by taking an axiomatic approach. Here is an example of 4 flavors of monotonicity axioms. So axiom 1 is simply the idea that adding an edge increases the centrality of a node, and lots of measures satisfy that. Of course, you can, with each such axiom, you can consider the dual axiom, and you can create artificial centrality measure which satisfy that one. A version of monotonicity basically states that nodes want to connect to nodes that are already in their connected component, and such properties are satisfied by a couple of other centrality measures. So our first sample result basically states that in the Jackson-Walensky model, suitably modified as we explained, stable networks look as follows. We have isolated nodes plus complete graphs consisting of nodes of type 2, plus at most one more complex component, which consists of 3 of the 4 types. Of course, there are nodes that don't want to be with anyone else, so those will not be part of any complex component. But the other ones, the ones that benefit edges, are going to be connected in a clique, and the ones that don't want to connect more to nodes in their own connected component, basically they're going to be pendant vertices. The picture changes significantly when adding finite thresholds, in that for every graph, one can set the thresholds such that the graph becomes an APSN. Our result also we give a complete characterization of APSNs for truncated centrality games with thresholds. However, the characterization in its most general form doesn't guarantee the existence of an APSN, and in a couple of cases where you have monotonicity plus some extra axioms, we can prove the existence of APSN via a greedy algorithm. A second kind of result deals with a different type of centrality axiom. Here the idea is that a node wants to connect to nodes whose degree is either higher or not too much lower than the one of the given node. And we have 2 flavors of this axiom corresponding to 2 different conditions. One is satisfied by Mihalov centrality, the other one by Banzhaf-Mihalov centrality. And the result in the paper states that under such a model of centrality measures, the stable networks have a rich club network structure in that there are a collection of cliques of widely different sizes. Basically, the nodes that are best connected are the ones that are connected between themselves. And then you have like middle nodes and nodes with even a lower degree, and at the bottom of the hierarchy you have isolated nodes. For the more restrictive version, basically the first parts don't appear, you only have isolated nodes. Perhaps the most interesting result in the paper is that we can characterize completely the kind of networks that arise as APSNs for games in which agents want to maximize between a centrality. Okay, you have a full condition here and an example of a graph which is non-bipartite, which satisfies the conditions. We also have in the paper some partial results, for example, for eccentricity centrality games. Here we have some necessary conditions, but we don't have a full characterization. And we've also looked at such games experimentally for a couple of measures. Here we've implemented some Python program using the NetworkX package, and simulations give rise to a bunch of conjectures, for instance, with eigenvector centrality or random walk between a centrality. To conclude, the paper studies a model of network formation, and the major advance to um, the Jackson-Walensky is that we've shown that one can make the model heterogeneous and still obtain mathematically tractable results. So you can get hopefully interesting results for centrality games where some nodes have one type of centrality, some nodes have a different type of centrality. We don't see our results as providing more than a start to such a investigation. We see it as a proof of concept that it is feasible to mathematically rigorously analyze centrality games where agents may have different types of centrality objectives, and we give many possible versions. See the paper for a couple of such suggestions. The paper has also a number of open questions. Perhaps the two most important open questions about such a model is we haven't figured it out. We haven't seen one example. We don't know one example where there is no APSN, in that you would have cycles, not fixed points, and would like to see if that is possible. Also, we'd like to modify the model to make it more realistic. Okay, that's it. Please ask questions by sending email or talking to us during the conference. Thank you.